In this video, I want to talk about Bayes' theorem. And what this is a way that we can take into account all of our information when deciding what the probability is. So we're going to do three examples, one over here, one over here, one over here. Try to not get too dizzy with all the stuff. So I'll just walk you through them. So our first question is, so imagine we have an urn that's some sort of a container that's full of three different kinds of shapes. And it could just be one of each of these three shapes. Okay, and so now you reach into the urn and you grab something. Right? So I'm going to reach in and I'm going to grab one of these. And then I could ask you, so what's the chance, oops, I made a mistake. Let me fix this. So I could ask you, what's the chance that you got a round object? And you would say, well, there's a 1/3 chance I got this one, and there's a 1/3 chance I got this one, so there's a 2/3 chance that I got a round object. This plus this is 2/3. Okay, but instead I could say, so you reach into the urn, and you get a green object. Now what's the chance, knowing that you got a green object, what's the chance that you got a ball? Right, because you have more information now. The chance that you have a round object has not stayed the same because now you have more information, right? For instance, if I told you that I could ask a simpler question, I could say, okay, you reach into the urn, you grab something. It's a black object. So now what's the chance that it's round? And you would say, oh, well, I know which kind of object I got because the only black object is the round one, so it's a 100% chance that it's round. Right, so in that case, obviously knowing that it's black changes the probability. But the same is the case for green. It's a little bit more subtle, but we want to update our probabilities based on our information. Okay, so how does this work? Okay, so we start and we have these three possibilities. And then I tell you, okay, you reach into the urn and you grab something and it's a green object. What's the chance that it's round? So what that means basically is that we can erase this one, right? Or if we do it from the pie chart, it means that basically we can erase this one. Because we know this didn't happen, right? And so we're left, now we only have 2/3 of our pie. And so now what we want to do is we want to take the piece of our pie that is the one that we're interested in, the round one, which is 1/3 of our total pie, and we want to divide it by how much of our pie is left, which is 2/3 of our whole pie. So what we're doing here is we're basically taking the probability of what we're asking, because I'm asking you, is it round? The probability of what we're asking divided by the probability of what we know, that we know it's green. Or another way to say that would be that we're taking the probability of our pie of interest, the pieces of our pie that are consistent with our question, divided by the size of our pie that remains after we get rid of what we know did not happen. And so we can also see that here. So the official way to do it, or the explicit way to do it, we could just take this. So here we would take what we know, 1/3, and we would divide it by the sum of everything that's left. 1/3 plus 1/3 is 2/3. So two different, well, they're the same method, but one is just visual with the pie, and then the other one is explicitly using our different paths. Okay, so I'm going to clean this up to get it out of our way. Okay, so now let's go to our second example. So in our second example, we're going to imagine an HIV test. Okay, so they're going to be taking a test for HIV, and let's say 1% of the population is affected, and 4% of tests for individuals that are not affected, we get a false positive. So we can do that by the method of paths. And so we have a 1% chance that we're infected. And if we're infected, we have a 100% chance of a positive test. A 99% chance that we're not affected, in which case we have a 4% chance of a positive test and not being affected. Or finally, not affected and a negative test. And so we can multiply these through, and we get 1%. And then this is 99% times 4%, which is very close to 4%. Let's just say 4%. And then here, 99% times 96% is very close to 95%. So we can do that by the paths, or we can do it by the pi. But then our question is, so we want to ask, what's the probability that we're infected? So if I just ask you the probability that we're infected, well, that's just this 1%. 1% infected, it's right there in the problem. Or I could ask you, what's the probability that you get a positive test? And you could say, basically, okay, well, not a negative test, but this is a positive test and this is a positive test. So it would be 1% plus 4%, 5% total. Or within our pie chart, we could say 1% plus 4% total, this 5%. But that's not really what we're going to be interested in. What we're going to be interested in is, given that we have a positive test, what's the chance that we are infected? And so we're going to use this bar, this vertical bar, and what this means is given. And so that means that we can simply write something like this. What's the probability that we are infected given that we have a positive test? Going back to our urn example, we could have said, what's the probability that the object is round given that it's green? Okay, so let's do this. So that would mean that we can erase, well, if we want to ask what's the probability that we're infected given that we have a positive test, we want to erase all the negative tests and just leave us with the paths that have positive tests, because those are the only ones that still concern us. Because we know in this question that we did not get a negative test. And so we don't have to think about the negative test anymore, we can just erase it. And so then what we're left with is 1% and 4%, so our whole pie is 5%. So what we know, the probability of what we know now is 5%. And then what we're asking is, are we infected? So out of this 5%, in 1% we're affected. And so we get something very close to 20%. So we've taken the probability of what we're asking, or what's the chance that we're affected, given what we know. We know that we got a positive test. We're doing the probability of our pi of interest divided by the entirety of the pi that remains. So let me clean this up. Okay, and so finally, we can do a pedigree problem. Okay, so we have a cross between two heterozygotes, and they have an offspring that is not affected. And so our question is, what's the probability that this individual is a carrier, big A, little a, given that they're not affected? Okay, so before we knew anything about this individual's phenotype, like before this individual was born, we would have these probabilities, right? Could be big A, could be big A, could be little a, little a. But when this individual is born and we observe their phenotype, now we can update our probabilities with our new information. And so that means that we can erase this little a, because we know that didn't happen because this individual is not affected. And so then what we're left with is this part where the individual is a carrier, so that's 1/2 of our total pi, divided by our total remaining pi, which is 3/4. So we can write that as the probability that the individual is a carrier, given that they're not affected. Okay, so the last thing I'd like to do with Bayes' theorem is to show the sort of most formal way of writing it. And this is generally how you'll see it. And so we're going to talk about two events, A and B. So this is confusing because we've been using big A to mean an allele, but now I'm saying A and B are both events. So an event in this case would be like the chance that would be the individual being big A little a or the individual being not affected. Let's see how this plays out. So what we're going to say generally is the probability of B given A is equal to the probability of A and B divided by the probability of A. So see how this works, right? Like here we said the probability of big A little a given that it's not affected. And then this was the probability, see this is the probability of big A little a. So actually we can rewrite this as the probability of big A little a divided by what we know, the probability that they're not affected. Probability of big A dash. So that's what we've done over here. So in this case, B is the probability they're a carrier. And so we've done probability of A and B, which is the probability that they're a carrier, divided by the probability of A, the probability that they are not little a little a. So this is our general way that we can write Bayes' theorem, and it works for a large number of different kinds of problems.